Hello, everyone, and welcome to the lecture on Numpy polynomials. So we've got our standard imports at the front, and we're going to go through creating a polynomial, plotting them, basic arithmetic between polynomials, calculus with polynomials, and then fitting a polynomial to a set of data. And all this is covered in the textbook as well as in the link at the top of lab 11 or 10, lab 10. To the documentation. So first off, what is the polynomial? A polynomial is just an expression in the form of, something times x to the 0th plus something times x to the 1st. It's with multiple terms. They're added up with multiple different x's. You all remember that from algebra and even earlier, probably. So what is a polynomial in NumPy? In NumPy, we have the polynomial helper convenience class, and this represents a power series polynomial. So something in the form of ax to the power of 0 plus b times x to the power of 1 plus ... Going on and on and on. There are other convenience functions that represent different types of series. Generally, for our purposes, the polynomial is what you want. So that's being imported right here. We also had some import errors in previous classes. So in Python, there's two ways, kind of three ways to import something. The first standard way is just import numpy. Second way, import numpy and then rename it. So here we're renaming numpy as np. That lets us just use np everywhere we want instead of typing out all of numpy. And that can be a lot of places. So that actually saves a good bit of time. And then there's the third type, which is from package name, import the class you want to import. So we just want polynomial from here. And that lets us say, rather than np.polynomial.polynomial, we can just say polynomial. So that's why we chose to do it this way. Generally makes your code a bit cleaner and a bit easier to write. So on to creating a polynomial. Let me clear this. When we first go to create a polynomial, we pass in an array with the coefficients. So if, for example, if we want to create a polynomial with 0 as the first term, and then 3 as the coefficient of the second term, and then 5 as the coefficient of the third, this should give us the polynomial 0 plus 3x squared, or 3x plus 5x squared. So when we run that, we can see it prints out right here, all nicely formatted, 0 plus 3 times x to the 1 plus 5 times x to the 2. So the first term of this list that we pass in is the coefficient of whatever term that index is. In this case, this term is the 0th position on the list. So it corresponds to the coefficient for the term that corresponds to x to the 0th power. 3 is to the first, or 3 is the first term. And so 3 times x to the first. 5 is the second, 5 times x to the second. Pretty straightforward there. And then when you go to print it, it shows up really nicely with this nice formatting down here. Next on to plotting. So following our standard way to create a plot, we can create the lin space. We want 100 or 50 things between 0 and 10. And then we can just go ahead and plot our x, and our polynomial is named p. So p of x. This is going to, just like your notation from algebra of you've got your x values and then your y values are f of x. In this case, our polynomial function is p. And so p of x, numpy went ahead and handled that for us. Then we want to show our plot. And we should see a nice quadratic up here. Looks about right on the range of 0 to 10. Let's make this negative 10 to 10. There we go. That looks more like the quadratic that we'd expect to see. And then to restrict the domain that we're viewing on, we could still do something like xlim. And maybe we only want to see this on -5 to 5. And there we have it here. The thing about restricting this using xlim is that -5 to 5 only gives us y values in this range, but the axes are scaled to give us y values all the way up to the maximum y value. So if we take away this xlim, we can see that the y values range up to around 500, a little over 500. And so we end up with this really squished looking graph when we're only showing it between 5 and 5. So generally, I like to limit the domain using a combination of limiting the x values that are going into the function, as well as using xlim. I think that generally these and these should match. And then we can see a more bigger graph that takes up more of the plot. It's a better looking plot. Now that's one way to plot this. There's another way that is generally considered to be a bit easier. And so that's using a different version of linspace, which is the polynomial linspace. So we'll say x comma y equals p dot linspace. And linspace takes in a number of terms. So we'll say we want just 5, and then the domain we want to graph it on. We'll leave that domain undefined for now. So what this is going to do is create an x and a y set of lists for us, and it's really just a plotting utility. So why don't we print our x and our y. We can see down here, our x is 5 terms between -1 and 1. That's the default domain. And our y is whatever the x value, like our y is p of that x value. So p of -1 is 2, p of -0.5, 0.25, 0, 0, etc. And on until we get to 8 over here. So this is a lot cleaner. You can see it's only 2 lines to generate the same chart. If you see the chart, we can actually plot dot plot x, y, and then plot dot show. Brand new chart, this time with only 5 terms between -1 and 1. We can take off the 5 and it'll give us the normal 50 terms, and we have a nice smooth graph. This graph went between -5 and 5, so it looked a little bit different. There's another way to use linspace. So what linspace returns is a tuple containing our x and our y values. What we just did here, where we assign those to 2 separate variables, that's called tuple unpacking, and it's a really common pattern in Python, where you'll have a function that returns 2 values, or you want a function to return 2 values, so you return them as a tuple. And then here we unpack them, saying the first ones are x values, second ones are y values. You can also do that inline by saying p.linspace and then saying you want to unpack them with this star symbol. So this asterisk in this case means unpack the tuple. And this should give us, I forgot to call the function. There we go, gives us the exact same graph. If you want to see what p.linspace looks like, you can print it out. We'll say n equals 5, so it doesn't take up everything. And then we'll print the unpacked one as well, the unpacked one. So this top one's the unpacked one. You can see it's printing 2 nice separate lists. And this bottom one is where it's still packed up. So you see it starts as a tuple and then gives us our first list and then our second list. But they're contained inside that tuple. So if you want to use it inline, you have to use the unpacking. Next, if we want to change our domain that we're plotting over using this linspace method, which is what I'll be using the rest of the demo. Oops. Domain takes in an array or a list. I'll use this interchangeably often. An array or a list here, -5 to 5. And now we can see this chart should match. Oh, we didn't do the excellent. There we go. So this chart should match this chart. It looks like they do. This is definitely a more concise, easier to write way. Hopefully it makes sense. If not, feel free to ask me about it in lab on Wednesday. You can also read the documentation. This p.linspace function is covered in the Numpy documentation. So what else can you do with these polynomials? Well, you can add them together. Just go ahead and get rid of this for now. Get rid of that. So first we'll print out our p, and then we could say make a new polynomial. Let's call it k. It's equal to p plus let's just add 2 to the first term. So if we think about what we're doing here from a math standpoint, we have this polynomial 0, 3, 5, and we want to add this polynomial 2. So this has 2 as the very first term's coefficient. So this polynomial is actually just the number 2. And so when we print our k should be now the polynomial that has 2, 3, and 5 as the coefficients. We could see that right here. We could also maybe add a bigger polynomial, let's say 2, -1, 4. A polynomial with even number of terms, and so that gives us 2, 2, 9, or maybe even a polynomial with more terms. And now we have 5 over here. So you can add polynomials together. Often Numpy will have overrides where you can, rather than creating this polynomial, if it's easier for you, you can just add a list. And it'll just figure out what you wanted to do there. So we added 3, 4. So 0 plus 3 is 3, and 3 plus 4 is 7. If you're not sure if it works, you can look it up, or you can just go ahead and try it in a simple situation like this and convince yourself that it works. You can also multiply polynomials together. So now we're multiplying our quadratic by a first degree polynomial. And that gives us, as expected, a third degree. With all the terms multiplied out. That's pretty dang convenient. And then you can integer divide. And so integer division gives us this. Outside of that, you can also perform calculus operations. So you can integrate and you can take derivatives. So if we want the first derivative, we'll say P1 is equal to P dot derivative. And we just want the first derivative. So the first derivative of, oops, should print it out first. The first derivative of this is this. You can see, 3 times the first power, and subtract 1 power, that gives us 3 as the first term. 5 times 2 gives us 10. You can also take the second derivative by changing this. This argument is which derivative to take. You see if you mouse over. That is not the right, there we go, deriv. Return a series instance of that is the derivative of the current series. So the second derivative we just get the number 10. Likewise, we can integrate. Or let's say, take the first derivative and then we'll integrate it back. I can't remember the name of that, so let's go over and check our documentation. Under calculus, integ. And so we integrate it and we get back this. Of course, when you integrate, we didn't supply a constant, so that first term is going to just default to 0, that new term. But you can see we went from this up to this. There's a lot more you can do with this calculus. I encourage you all to look at the function definitions for this deriv and integ functions. Finally, we've got fitting the data, and this can be a bit complicated and a lot of typing, so I broke my standard and I pre-wrote it out. But we've got this random data, which is just a list of 9 random points or something like that. And then we create our list of x values, which is 0, 1, 2, 3, 4, 5, 6. Just use the length of our y values for that. Then we fit a polynomial to this. That's using capital P polynomial from here, dot fit. Pass in our x values, our y values, and the degree of the polynomial we want. So we'll start with the first degree polynomial. And then we print our polynomial just so we can see it. And then we use our linspace, get our x and our y, we plot that. Then we're also going to plot our original seed data with little circles, and then we'll show that plot just so we can see how well we're doing. Great, so here we can see this is our first degree polynomial. It's a straight line because the highest degree is 1. And we've got our points. We can see this is kind of fitting, but like the error is pretty bad. It doesn't really look like the trend here. It looks like kind of sine wavy. So why don't we try increasing the degree to 2? And this is looking a little bit better, but it's still not really hitting it. It looks like we're going to need a 3rd degree polynomial. And here we can see this is much closer. This is looking a lot better. The error's a lot tighter. Could also try a 0th degree. Gives us a straight line across, it's just a constant. And you could do something crazy like a 10 degree, and I think we don't even have 10 points, so this is just gonna fit it perfectly. Of course, this is also almost definitely overfit. If we get any extra data, the odds are not great that this will be a great function for them. But this is not a statistics or a curve fitting class. This is just showing you how to take what you learned how to do in other circumstances and now do it really nicely and neatly in Python. You see, this is a great chart, and now you've got this polynomial. And these coefficients can give you interesting information depending on maybe these points are like airspeed velocity of a swallow or something like that. You're interested in acceleration. Great, well, I hope this was an informative lecture, and I look forward to seeing you all on Wednesday.